Hello everyone. Today we're going to talk about computational complexity theory, namely the big picture and how all the topics connect with each other. So the main goal is to explore the limits of computation at a large scale. So in terms of scalability, like at what point, what are limits of computation? When can we no longer compute something? And we analyze the inherent efficiency of solving problems. So we don't care about what language it's in or what particular computation model we use. We just look at a computational problem and inherently how hard is it to solve, how not hard is it to solve at scale, basically. So as an example, let's take the problem of list sorting. So list sorting has an input a list L, and as an output it has L but sorted. For example, if your list L is 3, 2, 1, 3, then the output would be 1, 2, 3, right? So it's a list by sorted. Actually, we don't have sets here, it's lists, right? So the order matters. So I shouldn't use the set notation here. So yeah, that's the idea of list sorting. Pretty simple, you've seen it before. But then how do we talk about the computational difficulty of this in general, independent of it? So we're going to care about whether there exists an algorithm that can solve it, right? We're going to say it's in P, and what does that mean for it to be in P? It means that there exists an algorithm that can solve list sorting in polynomial time. So what does that mean? Let's look at an example. For example, you've seen lots of algorithms that do list sorting. Let's have bubble sort. That takes time O of n squared. So as a quick reminder, what does O of n squared mean? It's if you have your input size here, n, that's your size of input. So in our example, that would be how many elements are in the list. And then this is how the time it takes, or you count the computational steps that it takes, depending on what your model is. And then, or you could just take the actual time measurements, right? So you run the program multiple times for different inputs, and you get kind of like a messy curve like that, right? And it kind of grows. And then the idea is, as it grows, as the input grows bigger, how much more inefficient will the algorithm get? And O of n squared means we can bound it above by some quadratic function. So we can draw some parabola here that bounds the execution times, right? That's the basic idea of it. And for the sake of complexity theory, usually we say that polynomial time is the most efficient one, even though in practice O of n squared might not be super desirable, but it's much better than the alternative. That would be exponential time, right? So O of 2 to the n, that grows so much more faster than O of n squared. Yeah, that's the idea. So yeah, because bubble sort is a polynomial time algorithm that solves the list sorting problem, we can say that list sorting is in P, right? So even though there are other algorithms that are more efficient than bubble sort, it doesn't matter. We just need an algorithm that takes polynomial time. And that means the problem is inherently in P, right? It means we can solve it in polynomial time. That's the idea. So then what's an example of something that's not as efficient as list sorting that we can't do in polynomial time? Well, let's look at the example of Sudoku solving. So if you don't know, Sudoku is a kind of puzzle. So the idea is you have a grid. To simplify it a bit, let's do a 4x4 grid, like this one. and it's divided into 4 boxes, and then inside you have so each box contains 4 smaller boxes, and then you fill them up with numbers. So you have 1, 4, 3, 2, 2, 3, 4, 1, and then the idea is you have to complete the numbers in the empty squares, but in a way that none of the digits are repeating either a row, in a column, or in a box. So it's kind of puzzle you might do. And then, for example, the output could be a solved version of this. So if we draw this out, so in order to solve it, we would need to, well, let's just copy the clues in first. And then a solution would be, I'm just going to copy the solution here. Right, so we might also be interested not just in, well, as an input we can have the initial puzzle, and then as an output a solved puzzle, but we might be interested in some other data as well. For example, how many digits can we use? So let's say part of the input is also, can we do it with 4 digits? Can we do it with 5 digits? Whatever. Then the output would be your solved puzzle, right? So the idea is, can we do this in polynomial time? Well, probably not. I guess we're not 100% sure whether we can do it or not. So far we haven't found any algorithm that does it in polynomial time. But we know it is in EXP. It takes exponential time, right? EXP. So that's similar to P, except that means we have an algorithm that does it in exponential time. And how does that algorithm do it? Well, the algorithm just brute forces it. So you kind of guess, oh, what would the number here be? And you keep branching off. And if the algorithm makes a mistake, you just backtrack and you make a different guess at that point. And that will take exponential time. Right? Yeah, so that's the idea. But then we know that, so it's in EXP, but then there's something, another property that's quite interesting about this, namely that even though it's really inefficient to solve it, we can actually verify it in polynomial time. What does that mean? It means that if given a solution, we can check that it is an actual solution in polynomial time. So in this case, we just have to check that the numbers match up in the correct squares and that this solution doesn't have repeating digits in rows or columns, right? So yeah, that's going to be pretty easy to, that takes just polynomial time because you're just comparing rows and columns of the object with each other, right? That's the rough idea, and that's what we call NP. So NP means we can verify it in polynomial time. Yeah, that's the idea. So then how do these connect up on a bigger picture? Well, it turns out if you can solve it in polynomial time, you can also verify it in polynomial time. So we know that P is a subset of NP, right? And it's going to be a subset of EXP. So that's where everything lives in, because if you can verify the solution, you can also guess the solution of this backtracking method every time. And that's just all the computable problems. It's a subset of all the computable problems. What do we mean by that? Well, it means that for each of these, we still assume that we can always find a solution on all inputs, and the program will not loop infinitely. It will not enter an infinite loop. It will terminate at some point, right? So even though it's very inefficient, the problems are still computable. And the problems that are not computable, we call them uncomputable. So those are the ones we can't guarantee to find a solution on all inputs on. So for the sake of complexity theory, we're not really interested in like the uncomputable problems. We're just interested in computable problems and how to make them, to solve them more efficiently. So there's a few techniques we can do. So the idea is, if we have problems in NP, how can we try and solve them a little bit more efficiently? What are different ways we can solve them, right? So there's three main techniques we use to solve NP problems. The first one is a reduction to known problems. So we're taking an object from one problem that we're asking a question about to an object of another problem that we already know how to solve, and we can just run that algorithm on it if we already have a pretty efficient one. But that doesn't really help you solve an NP problem more efficiently. It just helps you solve one problem if you know already the solution to another problem. So another thing is to use approximation algorithms. For example, greedy algorithms, they're usually an approximation. So what does that mean? It means you're no longer looking for the perfect solution, but you're looking for one that's good enough. And because you're no longer looking for a perfect solution, you can solve something more efficiently. You can solve it in polynomial time rather than exponential time. So the idea is, so yeah, for example, with the Sudoku, like an approximation algorithm would be, or maybe you get an algorithm that uses 5 digits instead of 4 digits. So in your solution you would have 5 digits instead of 4 digits, but we can do that really efficiently. Or just, it will be partially filled in, and the ones that are filled in, yeah. So it's like a solution that's good enough in your use case. So it's going to depend on your use case, what you think is good enough. And they usually use some kind of heuristics, and heuristics is just a guess you can make for what a good solution would be. For example, greedy algorithms, they just take the first best option that presents themselves, and very often that will give you a good enough answer. And then the final option is randomized algorithms. So these don't give you partially correct answers, but they have a chance of giving you the wrong answer, right? So if you have, so we have decision problems usually have yes or no outputs, and with randomized algorithms, there's a chance it will give you the wrong answer, like yes when it was a no, or no when it was a yes. And the idea with those is, usually we only have the error on one side, so it can only go wrong when it's a yes, for example. And by just repeating the algorithm enough times, we can be fairly confident with as much probability as we want to that it gives us the right algorithm, that it gives us the right answer. So yeah, the idea is there's a chance it might be wrong, but if we just repeat it often enough, it will still give us the right answer. And because it's much more efficient than a algorithm that always gives you the correct answer, it's still gonna benefit from the speed up, even though you have to repeat it many times, right? So you might ask yourself, well, if we can verify solutions in polynomial time, why can't we also find them in polynomial time? And that's actually an open problem. Like, we don't know if P equals NP or not. We think that probably it's not equal, but we don't know this for sure. This has not been proven. But yeah, that's kind of the idea. Should also mention there can be different variants for these kinds of problems. So we could have, so if you look at the most basic, most common one in complexity theory would be a decision problem. So what would the decision variant of this kind of problem be? It would be, does the puzzle have a solution with k digits, right? So that's a yes or no answer. So this will either output yes or no. That's what a decision problem does. This is usually the most useful one. And then we have the search problem. So for the search problem, the output would be a solved puzzle with k digits. So that's if you want to find the solution itself. If you're not interested in whether it's possible or not, but if you want to find a specific solution. And then you also have you have an optimization problem. So what would the optimization variant of this look like? Well, the output would be a solution using a minimal amount of digits k. So for optimization problems, there's some number you either want to minimize or maximize. So there's a number you want to optimize. In this case, for example, you could say, oh, we want to have as few digits as possible. So then k would no longer be in your input, but you would have a solution that minimizes the amount of digits needed, right? And then you also have a counting problem, so that the output would be the number of solutions with k digits, right? So that just counts something. And it turns out usually if you know the solution to one of these variants, you can find the solution to another of these variants. So they're all equivalent with each other. So very often we restrict ourselves to the decision problems because they're just much nicer to formalize to write down. So yeah, that's an idea of the big picture that you get in computational complexity theory. I hope you find this useful, and thank you very much.